Higher physics, particles and waves, the photoelectric effect. Key areas covered. Photoelectric effect is evidence for the particulate nature of light. Photons of sufficient energy can eject electrons from the surface of materials. The threshold frequency is the minimum frequency of a photon required for photoemission. The work function of the material is the minimum energy required to cause a photoemission. And determination of the maximum kinetic energy of photoelectrons. What we will do today is state what is meant by the photoelectric effect, state how frequency affects the photoelectric effect, state that a beam of radiation carries bundles of energy, packets of energy called photons, and carry out calculations on the energy bundles using the equation E is equal to hf. The photoelectric effect. Sometimes when electromagnetic radiation above a certain frequency strikes a surface, electrons are emitted. Remember, there's always electrons on the surface of materials, and particularly in metals, those electrons are free to move given enough energy. Normally, when an electric current is provided to a circuit, when energy is given from the supply, those charges will move. In the case of the photoelectric effect, light provides energy to the electrons, causing them to move and eventually separate themselves from the surface of the material. This can be used to detect radiation and is the basis on which solar cells and light-dependent resistors operate, as we looked at in semiconductor theory. The gold leaf electroscope. The photoelectric effect can be demonstrated using a gold leaf electroscope. Within the electroscope, we have a clean zinc plate, a non-metal rod, and a gold leaf. So our gold leaf is here. Now what happens is normally we would charge the clean zinc plate with additional electrons. Now because the zinc plate becomes negatively charged, the rod becomes negatively charged also, and because the gold leaf is attached to the rod at the top, it becomes negatively charged also. Now negative charges repel each other, so when the zinc plate is negatively charged, the gold leaf will move up. It's deflected. The more negative charge we have, the more the deflection is. If, however, at a later stage, we removed some of this charge, then the gold leaf would then start to move back down again. It wouldn't be deflected as much. So we can show electrons being removed from the surface of the clean zinc plate by how much the gold leaf has been deflected. If the gold leaf starts to move back towards the central rod, then that means that the charge is being removed from the zinc plate. So here are the results from the gold leaf deflection experiment. Only negatively charged electroscopes discharge, which makes sense. If we're removing electrons from the surface of the zinc plate and the surface is already positively charged, it's just going to become more positively charged because we're removing more electrons. Therefore, the deflection would only increase rather than the electroscope discharging and allowing the gold leaf to return to the central rod. Even dim ultraviolet light is enough to cause this discharge, and that's because ultraviolet light is a high-frequency electromagnetic waves, and we should know from National 5 that high-frequency electromagnetic waves, like ultraviolet, X-rays, gamma rays, are also high-energy waves. White light doesn't work, and that's because white light, the visible spectrum, has too low a frequency and therefore too low in energy. And we look at the relationship between the frequency and energy in the next parts of the video. So frequency. We can see that the photoelectric emission depends on the frequency of the photons, the frequency of the light. too low a frequency, we don't have photoelectric emission. We can't remove the electrons from the surface of the metal, which makes sense because those electrons are bonded to the nucleus of the atom. They need a reasonable amount of energy in order to break that bond. Below a certain frequency, called the threshold frequency, F0, there is no photoelectric emission. So we can think of the threshold frequency as being the minimum frequency of photon which would allow photoelectric emission to take place. It's important to note here a little bit about intensity. Now, intensity, irradiance, they're not really parts of the CFE higher physics course. However, they were parts of the old higher course, and they still appear within the CFE higher course as problem solving. Intensity is just really about how bright a light source could be. If you're dealing with something like ultraviolet radiation, which is not visible, it can be hard to tell how bright it is. Essentially, intensity is a product of the energy of each individual photon and the number of photons incident per square meter per second. So if we increase the intensity of a source, of the same source, we're not changing the frequency of the light, we're just changing the number of photons which are incident on the surface. So increasing the intensity at a given frequency, with that frequency being less than the threshold frequency, there'll be no effect whatsoever. So we can have a really, really bright white light on an electroscope, but it's not going to discharge because each individual photon of light from the white light doesn't have enough frequency and therefore enough energy to release an electron. However, if we increase the intensity for photons of light where the frequency is greater than or equal to the threshold frequency, we will cause more photoelectric emission to take place. They're directly proportional to each other. We can think of it like this. The photons of light are coming onto the surface. If the photons have enough energy, they release an electron from the surface. And it literally is one photon going on, one electron being removed. One photon, one electron, one photon, one electron. If we increase the intensity, that means we have more photons per second. More photons per second on the surface means more electrons released from the surface per second. So increasing intensity of photons when we have photons of sufficient frequency and sufficient energy means that we're going to get greater photoelectric emission. More electrons are going to be released from the surface per second. Now, if we think about the release of the photoelectrons as being a movement of electrons, a constant stream of these electrons being released, particularly if we can then move those electrons through a conductive material, leads us to the idea of a photoelectric current. So increasing the intensity means a bigger photoelectric current is produced. More photons per second, more electrons per second, which means more charge per second, which is more current, because current is the charge per second. So let's have a look at a question on the next slide. So here we have a question from the 2012 paper, question 15. We have a clean zinc plate mounted on insulating handles and charged. Different types of electromagnetic radiation are now incident on the plates as shown. Which of the zinc plates is most likely to discharge due to photoelectric emission? Now remember, in order for the electroscope zinc plates to discharge, first of all, they have to be negatively charged at the start, and then also the photons which are incident on the surface have to be of a high enough frequency. So let's go through one at a time. A. First of all, A is out because it's positively charged. So then I look through, I can get rid of C for exactly the same reason. I'm not even looking at the type of radiation incident on the surface. I'm looking at the fact that the zinc plates are positively charged, and I know they can't discharge. Now we're left with B, D, and E. Well, with B, we've got infrared radiation, not a high enough frequency, so B is out. For the same reason, E is out, because E is visible light, and that's not a high enough frequency. So our answer is D. We have a negatively charged plate which can discharge, and ultraviolet light which has a high enough frequency. So this leads us on to quantum theory. Does light travel as waves or photons? Well, we know that if we increase the intensity of light at frequencies which are above the threshold frequency, more photoelectric emission will take place. We explained that in the previous slide. The wave theory of light seems to disagree with this, as in wave theory we consider light to be a continuous wave, as in they don't change. Now, a continuous wave shouldn't produce more photoelectric effect as the intensity is increasing, because it should be exactly the same. However, in 1905, a scientist called Max Planck suggested that light doesn't travel as a continuous wave, but instead travels in packets called photons. And this led to the idea of quantum theory, along with Niels Bohr and Einstein. Modern physics now takes the view that light can act both as a wave and like a particle, without a contradiction in what it's able to do. It just depends on how we test it. Essentially, if we look for evidence that light is a wave, we test it by wave conditions, that's interference, reflection, refraction, diffraction. We will find evidence of these things happening. But also, if we look for evidence as a particle, for example, in the photoelectric effect, where it's acting like discrete packets of energy, we'll find that too. So in order to determine if something's a wave or a particle, we need to apply an appropriate test. And from further studies with Dirac and other physicists, de Broglie, we find that the universe seems to be made of things that are both particle-like and wave-like. In fact, the theory is that all particles have a wave function and all waves have a particle function. And this is known as wave-particle duality. Within the higher course, we focus on light behaving like a particle. Within the advanced higher course, we start looking at particles behaving like waves. But they're all part of the same branch of physics. That's quantum theory. So if we're looking for evidence that something is a wave, we'll find it. If we're looking for evidence something's a particle, we'll find it, as long as we apply the appropriate test. In order to eject an electron from the metal, we require a precise amount of energy. Now, this is all to do with electron energy levels, and we'll look at that in the further videos. However, we're saying that in order to release an electron, a specific amount, a specific quantity of energy needs to be given to the electron. A weak ultraviolet source has enough energy to do this for a clean zinc surface. And that doesn't matter how high the intensity of the white light is, no electrons are going to be ejected because they simply don't have that frequency. So the frequency must be related to the energy. The higher the frequency, the higher the energy. And if we have a sufficient frequency, we have a sufficient energy to reach that exact amount that the electron needs to be ejected from the surface of the metal. And this is true even if over a period of time we're providing loads and loads of energy in terms of white light. So we can provide white light, strong white light, intense white light for a long period of time, and we still aren't going to release any electrons. And that's because we need a specific amount of energy for each electron. In 1904, Einstein applied the earlier idea of Planck to a phenomenon and proposed that light was not a continuous wave but existed as a stream of packets or quanta, and that's where we get quantum theory. Now, these quanta are called photons, so we can consider photons being like particles of light, as well as other parts of the electromagnetic spectrum. Although, unlike other particles, photons have no mass. So instead of thinking of light as a continuous wave, as we see on the right-hand side of this diagram, we need to think of light being made up of little individual packets of energy called photons. And that is a key point. Now, each photon has an energy attached to it, a discrete amount of energy, and the energy of each individual photon depends on its frequency. So the energy of the photons is given by the expression E is equal to hf. Now, this expression is on your relationship sheet, where E is the energy measured in joules, F is our frequency in hertz, and H is Planck's constant, 6.63 times 10 to the negative 34 joules seconds. Now that's given in the datasheet. If you do enough calculations, you'll soon remember it. There is a useful rearrangement this though, and we need to think back to National 5, and we need to think back to our wave equation. So the wave equation is V is over F times lambda. Now if you think back to our dynamic universe, we're dealing with the speed of light because we're dealing with electromagnetic waves that all travel at the same speed, 3 times 10 to the 8. And in our dynamic universe, when we were looking at relativistic physics, we used the symbol c to represent the speed of light. And then we used it again when we were looking at nuclear radiations in the equation E is equal to mc squared. So using the equation V equals F times lambda, rearranging for F, and applying c as V, the speed of light, we end up with the formula E is equal to hc over lambda. Now this isn't on the relationship sheet, but it's really useful to know because sometimes we're given a question and we're told that this is microwaves or infrared or ultraviolet. We're not told explicitly what the frequency is, but we need to find the frequency in order to perform a calculation to determine energy. If we're given the wavelength of the radiation, we know it's part of the electromagnetic spectrum, using c over lambda, we can find the value for the frequency. Another equation which doesn't appear on the relationship sheet, but is also really useful, is one that used to appear in the old higher, and that's looking at the intensity of the photons. The intensity of light effectively is just a product of the energy of each individual photon multiplied by the number of photons we have. So each photon has a specific amount of energy. The more photons we have, the more energy we have. So the intensity is measured in watts per meter squared. So we think about this, the intensity being a measure of the number of photons per meter squared per second. So the per second per meter squared. And remember, the more photons we have per second, the more electrons we have per second. As I said, this equation doesn't appear on the relationship sheet, but it's really useful, and you'd be expected to understand what is meant by the intensity of light in terms of the energy of individual photons and the number of photons incident on the surface. The work function is a measure of the minimum energy of photon required to release an electron from the surface. Or we can think of it as the minimum energy needed by an electron to produce photoelectric emission. Either way, the work function is a measure of energy. If I give that amount of energy to an electron on the surface of a metal plate, it will be released. It's not going anywhere. It's just released from the surface. We know that the threshold frequency F0 is the minimum frequency of photon which will allow photoelectric emission to take place. So the work function is equal to hf0, hf being our energy of the photon, hf0 being the minimum energy of photon which will allow an electron to be released for photoelectric emission to take place. And each individual metal has a different value for work function. And these work functions would be given to you within the question in the paper. They're not contained within the datasheet. These are your key bits of information. Now let's assume we have a photon of light. The frequency of that photon is greater than the frequency threshold for that particular metal. Where does the extra energy go? The photon gives the energy it has to the electron to release it from the surface, but it still has more energy to give. That energy cannot be created or destroyed, so it has to go somewhere, and it goes to the electron to give it additional kinetic energy. And of course, if it has additional kinetic energy, it's going to move faster. So if the energy of the incoming photon, remember that E equals hf, is such that the frequency is greater than the threshold frequency, then the extra energy will appear as kinetic energy. So you can think about the three scenarios. You've got your metal plate. It has a work function, the minimum energy required to release an electron from the surface. Photon number 1 comes by. Its frequency is too low. Its energy is too low. The electron doesn't escape. Second photon comes along. Its frequency is exactly the same as the threshold frequency. Its energy is exactly the same as the work function. The electron is released from the atom, released from the surface, but doesn't go anywhere. Photon number 3 comes along. It has a frequency that is greater than the threshold frequency, an energy that is greater than the work function. So we use the work function energy to release the electron, and then any additional energy is given to the electron as kinetic energy. So the expression we have for this is Ek is equal to E minus E naught. However, we can substitute in our equations which we have for work function and we have for the energy of the photon to give us Ek equals to hf minus hf naught. And this is a very common question. You should be able to describe what's meant by the work function. You should be able to state how an electron ejected from the surface is given kinetic energy. And you need to be able to perform calculations using the formula Ek equals hf minus hf naught. So let's have a look at an example. The work function for gold is 7.84 times 10 to the negative 19 joules. A piece of gold is illuminated with light of a frequency of 1.5 times 10 to the 15 hertz. Will photoelectrons be emitted from the gold foil? So really, we're looking to see, does that light have enough energy? Now, in order to determine if it has enough energy, we need to compare it to the work function. In order to compare it to the work function, we first need to find the threshold frequency. So we have the work function for gold, 7.84 times 10 to the negative 19 joules. We know that energy is equal to hf naught. So F naught is going to be energy divided by Planck's constant. Substituting the values, we get a value of the threshold frequency to be 1.18 times 10 to the 15 hertz. So that means any frequency of photon above 1.18 times 10 to the 15 hertz will cause photoelectric emission to take place. We're told in the question that the piece of gold is illuminated with a frequency of 1.5 times 10 to the 15 hertz. So as that is the case, the frequency of the photons is greater than the threshold frequency, therefore photoelectrons will be emitted. Now this is a typical form of a calculation question. However, you also have some qualitative questions as well, describing the effects of changing certain values. So here, let's have a look at the problem-solving questions between intensity and current. Remember, if the irradiance increases, so does the number of photons per second per square meter. Therefore, the number of electrons emitted per second per square meter, and that means that the current, the flow of the electrons, also increases. So in this next example, we're looking at the 2007 paper, question 30. We have a typical setup where we have a metal plate, electromagnetic radiation is incident, and this is actually connected to a circuit so we can measure the photoelectric current. We're told the light of wavelength 605 nanometers is incident on the metal plate, and electrons are released with zero kinetic energy. Zero kinetic energy. So if electrons are released with zero kinetic energy, That means this light has just enough energy to release an electron and no more. That's the definition of the work function. The minimum amount of energy required by an electron to be released from the surface. Let's have a look at that first part. Show that the work function of this metal is 3.29 times 10 to the negative 19 joules. Well, at the moment in time, the only information we have is the wavelength, which is 605 times 10 to the negative 9 meters. And somehow we need to take this and show its energy. But that's okay, because we know that E is equal to HF, but we also know, we remembered that equation that's really useful, E is equal to H multiplied by C over lambda. So that's 6.63 times 10 to the negative 34 multiplied by 3 times 10 to the 8 divided by 605 times 10 to the negative 9, which equals 3.29 times 10 to the negative 19 joules. So we said that the energy of the photon is equal to 3.29 times 10 to the negative 19 joules. And we know that that allows an electron to be emitted and no more. That's the definition of the work function. We're asked to prove the work function is equal to 3.29 times 10 to the negative 19. So we've done that. In part B, the wavelength of the incident radiation is now altered. Photons of energy 5.12 times 10 to the negative 19 joules are incident on the metal plate. So we now have more energy released on the metal plate. Calculate the maximum kinetic energy. So EK is equal to HF minus HF naught. We're told that the energy of the photons is 5.12 times 10 to the negative 19 joules. And we saw in the previous part of the question, the work function is 3.29 times 10 to the negative 19. So the difference between those energies is going to be the amount of kinetic energy given to the electrons. So that's just going to be 5.12, take away 3.29, which is equal to 1.83 times 10 to the negative 19 joules. In the second part, we're asked about the irradiance. So the radiance of this radiation is now decreased. State the effect this has on the ammeter reading. Well, if the radiance has gone down, that means the number of photons per second per meter squared has decreased. Therefore, the number of electrons released per second is decreased, and the current decreases. Ammeter reading goes down. Okay, so this is a 2001 paper, question 19. Ultraviolet radiation causes the emission of photoelectrons from a zinc plate. The intensity of the ultraviolet radiation is increased. Which row in the following table shows the effect of this change? So if we've increased the irradiance, the intensity, we haven't changed the frequency of the individual photons. Now, if we haven't changed the frequency of the individual photons, we haven't changed their energy. Therefore, the maximum kinetic energy is going to stay exactly the same. So we can get rid of A, we can get rid of D, and we can get rid of E. Then we're looking at the number of photoelectrons per second. Well, if we increase intensity, we're increasing the number of photons per meter per second, and therefore we're increasing the number of photoelectrons per meter per second. Therefore, this is going to increase. We can get rid of C. So your answer is B. 2003, question 18. When light of frequency f is shone onto a certain metal, photoelectrons are ejected with a maximum velocity v and kinetic energy ek. When light of the same frequency and twice the intensity is shone on the same surface, which of these statements are correct? Let's go one at a time. Twice as many electrons are ejected per second. Absolutely true. If we have twice the intensity, we have twice the number of photons per second, and therefore twice the number of electrons ejected per second. Statement 2, the speed of the fastest electron is now 2v. Now this statement's incorrect. There should be no change whatsoever in the velocity of the electrons because there is no change in the kinetic energy of the electrons. We haven't changed the energy of each individual photon. We've only changed the number of photons incident per second per meter squared. So statement 2 and statement 3 are both incorrect. There's no change to the energy of the photon, therefore no change in the kinetic energy, therefore no change in the velocity. So we're looking at statement 1 only, which is A. 2004, question 15. Ultraviolet radiation is incident on a clean zinc plate. Photoelectrons are ejected. The zinc plate's now replaced by a different metal which has a lower work function. Remember, that means it needs less energy for an electron to be emitted. The same intensity of ultraviolet radiation is incident on the metal. That means the same number of photons per second compared to the zinc plate. Which of the following statements is or are true for the new metal? Statement number 1. The maximum speed of the photoelectrons is greater. True. Now the reason why this is true is because if we have a lower work function, that means the photons of light have more energy to give as kinetic energy. We're taking less of the energy of the initial photon on the surface to release the electron, so we have more energy to give as kinetic energy. If we give more kinetic energy to the particle, its velocity is going to increase. Therefore, statement 1 is true, and also statement 2 is true. Statement 3, there are more photoelectrons ejected per second. This is incorrect. We're told that the intensity of the radiation is exactly the same. Therefore, there are the same number of photons per second and the same number of photoelectrons per second. So statement 1 and 2 are only correct, which is D. 2006, question 17. When light of frequency f is shone onto a certain metal, photoelectrons are ejected with a maximum velocity v and kinetic energy ek. Now this looks very familiar, doesn't it? That's because it's exactly the same as a previous question. All they've done is jumble up the sentences. So you'll find that the SQA does that. There's only so many questions you can ask about the photoelectric effect, so we can repeat certain questions. They might be slightly ordered differently. Which of the statements is or are true? Well, we've got the same frequency, but twice the irradiance. Twice the irradiance means twice the number of photons per second, therefore twice as many electrons. Correct. Same frequency, though, means we have the same energy of photon. That means the same kinetic energy. Because the work function's not changed, we still are giving energy from the photon to release the electron, and the excess energy goes as kinetic energy. Unless we have increased the energy of the photons, we can't change the value of the kinetic energy. So statement 2 is incorrect. Statement 3 is also incorrect, giving us a correct answer of A. So here are some other past paper questions you can try to consolidate, looking at the old higher papers: 2000 paper question 28, 2005 paper question 29, and the 2008 paper question 29 also. And these are easily found with a quick Google search.